constant. It's m cubed, which is like not bad by the standards of some of your algorithms. If you took an Everest-sized black hole at the Big Bang, now we don't know why there would be, an Everest mass black hole at the Big Bang, we don't know why there would be such a thing.
What?
But a black hole that weighs the same as Mount Everest. Right. Then it would be evaporating around now. And actually, the final evaporation event is quite powerful because these things get very hot when they get very cold. And in the last few seconds of their life, these black holes give out about as much energy as all the nuclear weapons on Earth times a billion going off all at once or something. So it's quite
not as much as a supernova.
Very much not as much as a supernova. By the standards of astrophysics, not an incredibly violent event. By the standards of terrestrial weaponry, quite a violent event. And we could see it, we actually look for these things, and we could see an explosion like that if it happened anywhere within Pluto's orbit, and we've never seen it. So, within Pluto's orbit. Pluto, the dwarf planet. Yeah. Okay,
you couldn't see it further away easily.
You could not see it easily much further away than that.
Stellar distance.
If it was as far away as our sun, then you could see it. If it was as far away as Alpha Centauri, then I believe you could not see it. I'm going to hand over now, unless there's any pressing questions. Yeah.
So the equation you wrote, this is your definition of temperature?
This is the definition of temperature as a function of the entropy, just from thermodynamics.
Okay, but you know, like in classical thermodynamics, okay, I mean, I guess there are many ways of doing it, but like, at least the way I'm familiar with, like you first kind of have the temperature and then you define the entropy once you have temperature as a, like some kind of, integral between from like the zero temperature to whatever state you are, reversible heat.
That's what's happening here.
Okay,
you have a temperature that you compute from Hawking, and then...
Well, but you kind of started from the entropy and then you define temperature.
This is a good way. This is a great way to define temperature. It's telling you how the heat bath. It's telling you how the states, available states, change in the heat bath when you take energy out.
Right.
Okay, wait. So can you write a definition of the entropy?
Of the entropy?
Well, because otherwise it's like, it's an equation, but no. Okay, so I guess this is like what? Yeah, I guess this is related to Matthias's question. Like, what kind of entropy is this? Because on one hand you're saying it's kind of like the classical thermodynamics entropy.
It's like a coarse-grained entropy, yeah.
What does that mean?
It is the same sense in which if you took a big vat of gas at a temperature T, it's
now you have temperature.
But if you took a big box of size L cubed, volume, and temperature T, you know that the entropy would, the Stefan Boltzmann law tells you that the entropy is given by that formula with some number here. So this is the Stefan Boltzmann law for what the entropy of a vat of gas is. And this law is true even if the vat of gas is overall in a pure state. Because this is not the von Neumann entropy. The von Neumann entropy of that vat of gas would be 0. This is the coarse-grained entropy. Why am I interested in this coarse-grained entropy? Answer, because this is the thing that goes up or stays the same according to the second law of thermodynamics. The coarse-grained entropy will not increase of this gas. It's a constant. So the fine-grained. The coarse-grained entropy is the thing I'm interested in if I want to do thermodynamics and keep track of the entropies.
Here you have a temperature, because from Hawking you calculate the temperature, so
yeah.
And you know that how the temperature scales as a function of mass, you can compute the entropy by that definition.
Yeah, so
it goes the other way around.
The historical history of this is that this is the thing that was, with the tilde, is the thing that was conjectured first. Then Hawking pointed out that that couldn't possibly be true, because that would mean that black holes had a temperature, according to this formula. Then Hawking calculated the temperature of the black hole and got exactly this answer. And from that, you can then go back and plug in the number here. So historically, that's the way, that was the intellectual progression from entropy to temperature back to entropy.
Okay.
Yeah?
Sorry, just to understand if I understood correctly the argument you made before. So if I take a bunch of normal matter, so its entropy will scale initially like with R cubed.
Correct.
But this would be still much lower than the R squared
Right.
because of the constants.
Correct. This would be a
At some point, if I put enough matter,
yes.
it will revert to a R squared
Correct.
scale.
Correct.
So, okay, so there would be a regime where it tends
There would be a regime where it was growing like R cubed, but in that regime, the prefactor would make it,
yeah.
would
But
kill
is
you.
there any so is there any possibility that objects that are not of the size of, I mean, is there any way to see this transition in any reasonable experimental situation where you transition from this R cube scale into the R square scale?
Experimental,
In the cosmos.
yeah, in the cosmos.
Yeah, like the entropy of Jupiter is proportional to its volume.
Correct.
If you kept making it bigger
Yeah,
until it was 10 times the diameter of the sun, it wouldn't do that anymore.
yeah. So I don't know if you accept that as a reasonable experiment, but that's,
And nature might
Yeah.
choose to do that.
right. Okay, so this is black hole thermodynamics as it was understood in the 1970s, and it's thermodynamics. Now the quantum information people get involved and start asking questions like, if I start off with a pure state and I collapse it to form a black hole and then it evaporates and I wait around for 10 to 55 times the age of the universe and it evaporates and I collect all the stuff, is it still are all the remnants, the Hawking radiation that's come out, is that stuff all still in a pure state? That's called the information puzzle, and I'm going to hand over to Jonathan at this moment.
I have a question regarding.
Okay.
Didn't we just learn before? Oh wait, we had this discussion.
I think we
should,
should.
no.
Yeah.
Yeah, but I was just gonna. I mean, aren't we alone by that time? I mean, don't we often see nothing apart from like our 10 to 55 times light?
This is
You-
doesn't depend on observers. Like,
Right.
he's asking a question about physics here. I mean, I think observers are important too.
Right. You want to know what the universe looks like in
But I
10 to
can't
55?
connect it because I mean,
Oh, so you're worried that whether you could actually do this experiment?
yeah, I can't do it right because I only see my own sun anymore in 10 to 55 years.
Well, the sun will be gone in
Okay, sure, but like I don't even see my sun. But,
Well,
but
we
the
might-
rest will have my
we might have-
likewise and will be like too big.
So
Too small.
you're worried about the fact that dark energy will cause the universe to expand so rapidly that we'll
Yes.
get ripped apart from the other structure in the universe.
And I can't do this anymore.
Well, first of all, you could formulate this problem in Minkowski space if there wasn't dark energy, and it's not clear that dark energy should affect the story. But in any event, dark energy will not unbound us from the rest of the galaxy. It'll only unbound our cluster from other clusters. So,
Dark energy isn't strong enough to pull you away.
Okay, so
from Earth.
we could see it in our galaxy.
right, and there are plenty of black holes in our galaxy. I mean, you're thinking of a more sort of hands-on practical application than I think would be typical of people who worry about this problem. But if you want to do the engineering challenges, I'd be happy to. I mean, the real engineering challenges is that you need to capture all the gravitons that are emitted in Hawking radiation from a black hole and hold them in coherent superposition with these ideas.
Oh, yeah.
So nice question, maybe leave it for later. It's maybe more for you, Jonathan, but I got stuck how you said that the black hole is absorbing stuff and initially vibrate and, release high order stuff. So then this high order stuff like bounce back the information of the stuff that it absorbed into the gravitational field or something, because I guess it will propagate.
It will certainly emit some information, but you can calculate whether that's sufficient to carry away enough information. So you're leaping ahead to the information puzzle, and if you calculate how much entropy that will carry away, not enough to explain the whole entropy of the black hole.
But like say this LIGO result where we've got these two black holes that
Yes.
merge. If you collected all those gravitons and focused them back in, it would cause the black hole to spin apart and fission, right? It's reversible if you believe the unitary.
Yes, but to do that, that is true. But to do it, you really have to collect all those gravitons.
Yeah,
and send them-
every last yeah.
you'd have to send them back in coherent quantum superposition.
Yeah.
But that's, you're
Okay.
speaking Maxwell Demon, right?
an engineering challenge.
Yeah. It is reversible, but.
So I was just going to present the version 1 black hole information problem, and then the version 2, which is sometimes called the AMPS experiment. And then,
Firewall, right?
yeah, we were discussing that maybe the word firewall, the fact that it's called the firewall paradox, maybe is confusing to people because it makes them think that the paradox doesn't involve firewalls. The paradox is about monogamy of entanglement, and one potential solution is that there's a firewall. So maybe that's a better way to say it. And then maybe people like Adam and other people can just kind of chime in as well. And maybe I'll present it first, and then people can. I feel like people are already asking questions about the information problem. But so we could just do it like that. But so the version 1 was due to Hawking, and it's effectively, I can imagine, for example, either creating a black hole from a pure state. So I take a shell of dust that is in a pure quantum state, and I form a black hole out of it. And then I let it evaporate. And if we believe that Hawking's calculation is true, then it should evaporate thermally, and we'll have a pure state which goes to a mixed state. And that would contradict at least the unitarity of quantum mechanics. And that's all, maybe. And I guess what maybe you might imagine could be happening is that somehow this thing is radiating, but it's like a lump of coal radiates, and so it looks thermal, but eventually it has to evaporate back into a pure state. So I have a black hole. I form this into a black hole. It evaporates away until we have nothing left but radiation, and the question is that radiation in a pure state, or is it thermal, fundamentally thermal? If we believe it's like a lump of coal, then everything should come back. So all the entropy should come back. So if we now look at, if we look at the radiation as a function of the number of photons that come out of the black hole.
Fine-grained entropy.
This is now, yes, so Matthias, this is the von Neumann entropy of the radiation. And so what we would expect to happen if this was a lump of coal, if a black hole was a lump of coal, is that initially there's no radiation, we just have a lump of coal. We now collect some the black hole, the lump of coal radiates away, and so the entropy of the radiation is increasing linearly with the number of photons. This is called the Page curve, what I'm drawing. But then we know that at the end of the evaporation process, purity has to be restored. So this is entropy of R. Purity has to be restored. And so what we would expect to happen for a lump of coal is that somehow in all the correlations of the late time photons which are being emitted, by late time I just mean photons emitted after the Page time, which is this peak here, the state has to become pure. So there's got to be subtle correlations in the photons as they leave the lump of coal or the black hole that they will somehow restore purity to the photons which have been emitted at early times. So this is the kind of, it's called the Page curve, and this is how we think a lump of coal behaves. And the question is that how a black hole behaves? Is that what's happening with the Hawking radiation, that the late time photons are coming out? I'm just going to jump to version 2 of the black hole information problem. It's just easier. Is that a good idea, Adam, or should I? Yeah.
Do you have any questions on version 1?
Yeah, what's wrong with version 1?
What's wrong with version 1?
I mean, suppose somebody says, yes, that's how black holes must behave.
Right. So I guess version 2 I think makes it much more clear why there's going to be a problem with this picture.
So people thought you had to trace out the interior. Is that why this was paradoxical? That you had to trace out the interior of the black hole, so it was mixed for a while and then.
Yeah, I mean, so if we're just looking at that, so what we expect to happen is that these photons, the thing Hawking evaporates, these photons come out. There's a black hole here, and eventually the black hole disappears, and there's nothing left. So eventually, there's just radiation. Now, it may be, I think, by tracing out the black hole, maybe you mean that evaporation stops, and this thing just becomes what's called a remnant. It just, at some point, it just stops evaporating, and then it may be that if it stops evaporating at some point, then we just have thermal radiation out, and the thermal radiation is purified by this remnant of a black hole. That's a possible solution to the black
So
hole.
this is
I guess
another
I'm
area.
trying to understand why it was considered paradoxical, because, you know, you have a big closed system that contains the black hole and the radiation.
Right.
Everything is coherent and pure, and
Yes.
it's never actually,
The reason it's paradoxical is that there is an important difference between a black hole and a lump of coal. With a lump of coal, there will be no paradox. It will just work exactly as Jonathan has described.
Right.
With a black hole, the confusing thing is that the information that you threw in the qubits out of which you formed the black hole, according to classical gravity, just sails right on past the event horizon and gets lost in the singularity and can't get out from the singularity. On the other hand, if you believe what apparently on the face of it is the calculation that Hawking did that describes Hawking radiation, the Hawking radiation does not come from the singularity. The Hawking radiation comes from the event horizon of the black hole. And you can't, and so the question is, how did that information, if you believe in causality and all the rest of it, get from the singularity deep in the black hole all the way to the event horizon in order to then be carried out by Hawking radiation? And to do that, you need to go faster than the speed of light. So, not only can you not get out from an event horizon, you can't, once you're inside the event horizon, you can never even get to even slightly larger arc. You just get swept downstream by the thing, and then your gravitational field gets stronger and stronger and stronger. So